Okay, question 24. So, rectangular plastic block, how can you use it to work out the refractive index? So you've done this experiment at school, so you've got a space here to draw a diagram, so you should probably take advantage of that and show the ray of light coming in, refracting, carrying on back out in the direction it's in, then draw yourself a normal line, which is important, label the angles, angle of incidence, angle of refraction, or you can use theta 1 and theta 2, it's up to you, and then just make the point that the refractive index is then sine I divided by sine R. And in actual fact, just drawing that diagram and writing that formula gets you 2 out of 3 of these marks, because that's the main A-level point of this, this question. The extra third mark will come from you providing any extra details. So for instance, I won't write it now, but you could add it, that either you need to use a protractor to measure these angles, or that you need to use a really narrow beam of light, conduct the experiment in a really dark room. If you wanted to, you could say do it for multiple angles and get multiple values for this and take an average, or even better, take multiple values and plot a graph of sine I against sine R, and that should be a linear relationship, and the gradient of that graph will be the refractive index. So take advantage of spaces to draw diagrams in, because it can save you a lot of words. What you don't need, by the way, for this question is the kind of stuff that you would have written at GCSE, which is more methodical explanation. So you, at GCSE, you'd have written something like put it on a piece of white paper, trace the ray with a dashed lines, take the block away, put the ruler down. We're going to assume that all of that is very easy for an A-level student, and really what you need to be pointing out are the A-level sciencey bits, and also the technical bits where they might screw up if they weren't being careful, the experimenter. Okay, so on to part B. We're bouncing a pure frequency of sound waves off a wall, and it's coming back, and there's being some interference, and that's, if we get the loudspeaker at just the right frequency and just the right distance, we're getting a pattern of nodes and antinodes in this gap. So maybe the wave would go in and then bounce back, and then we'd have node, antinode, node, antinode, node, antinode, node. And what we're doing is we're moving a microphone along this gap, and it'll go quiet, loud, quiet, loud, quiet, loud. And what we're doing is measuring the distance between adjacent antinodes, which is the distance that they're referring to as L here. And just for what's about to come on, notice that the distance L is going to be, what are we measuring? Oh no, between adjacent nodes, sorry, not node to antinode. So notice that the distance L here is half of a wavelength, so L equals lambda over 2. Okay, so now that we understand what's going on with the experiment, we're just going to see what they want us to do. So draw a line of best fit and get the gradient of the line. So stick a line on that. And then again, use as big a triangle as you can possibly get it. The examiner's been very nice to you and given you a line that happens to go very nicely through 0. So we can use this big triangle here. So that's 17.5, and that's 3. 3000, don't forget the K. So gradient will be change in Y divided by change in X, which is 171. Okay, explain why the gradient of the line is v over 2, where v is the speed of sound. So before I even do anything, I'm just going to check to myself that I know the speed of sound is around about 330, 340, and so if I double that, will I get 330, 340? And the answer is yes, I do, which makes me feel that I probably did do the gradient bit right. Okay, so why is it? Well, the gradient is f divided by 1 over L, which is FL. And we already noted that L was lambda over 2, so that's F lambda over 2. And then we remember the wave equation, that V equals F lambda. So that's why we've got that. So gradient is indeed V over 2. We would get 1 mark, I guess, for some version of what the gradient is algebraically, and then another mark for showing the relationship from the wave equation. Okay, so the next part of the question says use the information to determine V. Well, we just said that the gradient was half of V, so we just need to double the gradient. And that gives us, what, 342, which is our speed of sound. And then last part of the question, smaller values of L are much more difficult to determine with the microphone, and this produces a large uncertainty. How could we fix this? So the problem here is that L is small. We might be measuring with a ruler that has millimeters on it, and if we're measuring 20 centimeters, a millimeter of uncertainty is very small compared to 20 centimeters, but it's not small compared to 5 millimeters. So we just need to make L bigger, basically. So the easiest way to make L bigger is we can measure multiple nodes. Instead of adjacent nodes, we could maybe do 3 nodes, and then that will give us a much bigger L, and that gives us a bigger L. It says suggest how it can be reduced, so we just need to be really crystal clear about what the effect is. If you didn't want to measure multiple nodes, you could have reduce the frequency. So remember, V equals F lambda. So V is fixed, it's the speed of sound in air. If we make F go down, then lambda will go up. And remember, lambda is effectively what's defining L. So if we take the frequency down, the wavelength, and therefore L will go up. So that was an alternative answer. And then I suppose if you really wanted to get into the nitty-gritty of it, you could say get a smaller microphone so that you can fit it into the smaller nodes more accurately. But these are the answers, one of these two, that are easier to express. So I would stick with one of those if I were you.